Okay, let's talk about adding and subtracting rational expressions. Now, to add and subtract rational expressions, we're going to do essentially the same exact thing that we do when we add or subtract fractions. So let's take a look at how we do that first. Of course, you'll remember if we have a fraction like 2/3 plus, let's say, 3/5, in order to add those two fractions, we'll need to get common denominators, right? And to get the common denominator, you probably would just say, well, that's 15. That's the product of 3 and 5. And sure enough, you'd be right. You had to write this as something over 15. That would be 10/15. And you'd have to write this as something over 15. Well, let's see, that would be 9/15. And then you could add them straight away, and there's your answer. Everything's great, right? However, this process breaks down a little bit when we look at something like this. 3 over 490 plus 2 over 525 equals, well, again, we've got to get common denominators, but what is the common denominator here, right? This is a lot more difficult to solve for the common denominator by inspection than the previous problem was. Fortunately, there's a nice simple way that we can do this, that we can carry over to rational expressions, because when we're dealing with rational expressions, finding common denominators just by looking at it is difficult as well. Okay, and the trick here is factor. Look, 3 over 490, that's clearly divisible by 2 and 5. In fact, if we come up with the factorization here, that's 2 times 5 times 7 squared. Okay, factor the 525. So that's going to be, here again, it's divisible by 5. Matter of fact, we can take a couple of them out, and if we do that, we quickly see the factorization is 3 times 5 squared times 7. Okay, we would like these two denominators to be the same. So ask the question, what is this denominator missing that this denominator has? Right, so clearly it's missing a 3. It's got one 5. There's a second 5 over here it's missing. So a 3 and a 5, and it's got two 7s. This one only has a single 7, so we don't need to add any more 7s to it. But it would be really good if I had an additional 3 and a 5 over here. So put them in. Let's multiply this by something where we get an extra 3 and a 5 in the denominator. Of course, if I'm going to not change the expression, I better be multiplying by some well-chosen value of 1 here. So let's multiply by 3 times 5 over 3 times 5. And in a like manner, now let's turn our attention to this guy and say, what is this denominator missing that this denominator has? Okay, so we certainly got our 3 here. We've got 5 squared. There's a 5 there, a 5 there. We've got a 7. Okay, there's a 7. But this denominator is missing a 2, and it's missing a second 7. So put them in. Let's multiply by some fraction here where we pick up an additional 2 and a 7. Of course, here again, I don't want to multiply by anything but 1 lest I change the value of these fractions. So I'm going to multiply by 2 times 7 over itself. Okay, now looking at the denominators that are going to result, it's just the product of 2 and 3 and 2 5s and 2 7s in both cases. Voila, instant common denominator, and I don't even know what that product is. But I can write it immediately as 3 times 3 times 5, right there, that's that product, plus 2 times 2 times 7, there, that's that product, over the common 2 times 3 times 5 squared, right, we have 2 of them, times 7 squared. Here again, there and there. There's our common denominator. And from here it's a breeze. 3 times 5 is 45, right? Plus 2 times 2 is 4 times 7, that's 28, over this common denominator. And 45 and 28 is 73. Okay, over this. Okay, which of course we could crank out. You may wonder why I kept writing this product all the way through rather than going ahead and multiplying it out at this step. But think about it. You're going to find this product, you're going to find this product, you're going to add those two things together, you're going to get some sort of value here. In the next step, what do we have to do? we have to simplify. We have to reduce this fraction to lowest terms. That's going to require factoring the top and factoring the bottom to see what common factors they have. We already have the bottom in factored form. Let's just leave it that way. Let's be a little lazy here and wait. Okay, otherwise we're just going to have to go back and refactor it. Right? 73, as it turns out, is prime, so nothing cancels. So we are safe now in multiplying this out to get 7,350 and being assured that this is in lowest terms. Okay. So it's this process, that we used here for this second addition problem, that we'll use with rational expressions. We'll factor the denominators involved. We'll ask the question of each. What is this guy missing that the other one has? And what is this guy missing that the other one has? And we'll put them in. We'll insert those factors that we want by multiplying by a well-chosen value of 1. Okay, and then we'll do the necessary multiplications and additions, canceling if we can, to get our final answer. All right, now let's see how this plays out in terms of rational expressions. Example 1. Suppose we wish to add 1 over x, nice tiny simple rational expression, and x over x plus 2. Okay, so as we said before, we want to make sure the two denominators are completely factored, but here they actually are already. Okay, if you want, you can put parentheses around that. Now we ask the question, what is this denominator missing that this denominator has? Well, this has an x, this is an x plus 2, so it's clearly missing an x plus 2. Let's insert it by multiplying by x plus 2 over itself. That's a well-chosen value of 1. Plus x over x plus 2. What is this denominator missing that this denominator has? Well, clearly the factor of x. So again, let's put it in. There's an x. We put an x on the top as well, so we're really just multiplying by a well-chosen value of 1. Now look at the two denominators that are going to result when we multiply these guys together. You have x times x plus 2 here, you have x times x plus 2 here, that's a common denominator. So we can say 1 times x plus 2 is x plus 2, plus x times x, that's x squared, over the product, the common product here of x times x plus 2. Okay, maybe clean it up a little bit. We could write this in descending order, standard form here. X squared plus x plus 2 over x times x plus 2. And then all that remains is to look at this numerator and say, hey, does this factor? Because if it did, and there was a common factor down here, I could cancel it. But x squared plus x plus 2 doesn't factor, does it? We can do a little scratch work off on the side here. Probably we'll have x's and x's. We need a 2 and a 1 to get that 2. But this tells us they're the same sign, and whether these are both positive or both negative, I'm not going to get positive x. Okay? So that doesn't work. This doesn't cancel any further, and that's our final answer. If we want, we can expand the bottom just so that both the top and the bottom are in expanded form. Often, you'll find it more convenient to just end on this step. But we'll go ahead and flesh it all the way out. Okay, and that is that sum of two rational expressions. Now let's take a look at a more complicated example. Example number 2. X over x squared minus 4 plus 1 plus x over the quantity x squared plus 3x plus 2. Okay, so what can we do here? Here again, in order to add these two rational expressions, I need common denominators. In order to get the common denominators, I want to look at the factors of each. So let's rewrite this where the denominators have been factored. Of course, this is x squared minus 4. That's a difference of two perfect squares, x squared and 2 squared. So we can factor that into x plus 2 and x minus 2. Over here on the right, we have 1 plus x on the top. And then down below, we have a trinomial. We'll guess that it breaks into two binomials. We've got an x squared there. That probably means we have x's there and there. We've got a 2 here. There's not too many choices there. We could have a 1 and a 2. They could both be positive or both be negative, but they have to be the same sign because of that positive. Remember, the product of these two values gives you this. And we need a 3x in the middle. If I make them both positive, notice my inner product is x and my outer product is 2x, so I get 3x. Yay, we got them factored. Now, to find the common denominators, we have to ask ourselves the question, what does this denominator have that this guy is missing? And vice versa. Okay? Well, we've got x plus 2. He's got an x plus 2. He's got an x plus 1. Oh, wait a minute. We don't have an x plus 1 over here. Okay? That's what we're missing from this denominator. Or in this denominator. So let's put it in. I'll break it into a separate step this time. So I have room. We're going to multiply by some fraction that has that missing x plus 1. Of course, we want that fraction to be a 1, a well-chosen value of 1, so that I'm not actually altering the expression. Plus, let's see, we had 1 plus x over here on this side over x plus 1 times x plus 2. Is he missing anything? Well, this guy's got an x plus 2. He's got an x plus 2. This guy's got an x minus 2. Uh-oh, we don't have an x minus 2 over here. So let's put that in. Again, over itself, so we're really multiplying by a well-chosen value of 1 there. Okay, now, after the multiplication here and here, we'll have the same common denominator. So I can rewrite this as x times x plus 1. That's that product. Plus 1 plus x times x minus 2. That's that product. All of that over the common product, common denominator of x plus 2, x minus 2, and x plus 1. Okay. Now, just like before, let's do the multiplication and add those two guys together. This, of course, is x squared plus x, distributing that x to both of those terms. Over here, we can FOIL things out, or just look at all four possible products here. We have an x times an x, that's x squared. We've got a minus 2x and a plus 1x, so that's minus a single x net. And then we got a 1 and a negative 2, so that's going to be minus 2. All of that over the common denominator again. Okay, of course, we get some cancellations up here too, don't we? Positive x cancels with a negative x. And x squared combine together to give us 2x squared. And don't forget the minus 2. Okay. Remember, we left this and continue to leave this denominator in factored form because it is possible that the numerator, when we're all done with all this multiplication and addition, collecting of like terms and so forth, it's possible that numerator factors and we might have a common factor that we could cancel off. Does that happen here? This is 2, right? There's a 2 in both of those guys, times x squared minus 1. Hey, that factors further, doesn't it? That's a difference of squares over that mess. Okay, let's take this over here so we can finish it up. Again, 2 times x squared minus 1. The x squared minus 1 is a difference of squares. Let's factor that. That's 2 times x minus 1 times x plus 1 over x plus 2 times x minus 2 times x plus 1. Aha! There's a common x plus 1. Nothing else seems to cancel. Okay? So we could either leave it in a factored form, I have 2 times x minus 1 over x plus 2 times x minus 2. That will suffice as an answer. If you need to expand it all out, you can certainly do that as well. So that'd be 2x minus 2 over, down here, that's the difference of squares, which multiplies rather quickly. Either one of those two is, again, fine. Put missing equals up there. Okay? All right, let's look at one more example. Okay, example 3. This time I want to put 3 things together. 3 rational expressions. 1 over x plus 1. The trivial rational expression of x. Remember, that's just x over 1. And then x squared plus 2 over x squared minus x minus 2. Okay? So, here again, if we want to combine these, we need common denominators. In order to get common denominators, I need to see all the denominators factored. So the first thing I might do here is just put that over 1, just to remind myself that 1 is the denominator. And then the second thing we can do is say, well, does x plus 1 factor? No. So it's already in completely factored form. Might put parentheses around it, just kind of keep track of that. Certainly there's nothing we can do with the 1 here. But this one we can do some stuff with. Let's see, it's a trinomial, so let's try breaking it apart into 2 binomials. We have an x and we have another x. To get that 2, we'll probably need a 2 here and a 1 here. It's a negative 2, so they'll probably have to be different signs. And we want the inner and outer products to sum to give us a negative x. We can make that happen by making that negative and that positive. Okay, now everything is factored in terms of the denominators. And I just have to ask the question, what is this denominator missing that any of the other denominators have? Okay, any of them. So I look over here, well, there's not much in that denominator. It's a 1, there's an understood 1 as a factor there, so I don't need to worry about him. Over here, we have an x plus 1, but we have an additional x minus 2. So let's insert that. Actually, I'm going to come all the way over to here. So that's going to be 1 over x plus 1 times x minus 2 over itself. There's our well-chosen value of 1. Maybe put things in parentheses so it's a little more readable. Plus, we have x over a 1. Same question. What's this guy missing that any of the other guys have? Well, he's missing everything, right? There's an x plus 1 he's missing from here. There's an x minus 2 he's missing from here. This x plus 1 is already accounted for by this one. So we need to multiply by a bunch here, x minus 2 and x plus 1. Okay, so he's taken care of now. Plus, let's see, we start off with x squared plus 2 over x minus 2 times x plus 1. Same question. We need to pick up anything that this guy is missing that any of the other denominators have. But he's got an x plus 1, and he's certainly got an understood 1, so he doesn't need any additional factors thrown in there via a well-chosen value of 1 multiplication. If you look at all the denominators, now everybody is the same. So I can write this as x minus 2 plus the product of those 3 things plus this last thing over the common denominator of x plus 1 times x minus 2. Okay? Now, all we've got to do is clean this top up. There's some multiplications we can do, some collecting of like terms that we can do to get this down to something tighter that we can then check to see if it cancels, if any of its factors cancel with what we have on the bottom. Okay? So let's do the multiplication first. We have an x minus 2 sitting right here, plus we've got the product of x and x minus 2 and x plus 1. Those two I could just FOIL out together, right? Multiply them using that little FOIL mnemonic. So that'd be x squared minus 2x plus a single x would be minus 1x. And negative 2 times 1 is going to be negative 2. But then when you multiply by x, all these guys go up a degree, right? So x squared, get change to x cubed. This becomes x squared. This becomes 2x. Okay, and then we have our plus x squared plus 2 on the end there over x plus 1 and x minus 2. And then we look for some collecting of like terms. Negative x squared and positive x squared drop off. We've got an x minus a 2x. That's going to collect. Negative 2 and positive 2 also drop off. Let's see, so it looks like we're left with x cubed. X minus 2x is negative x. And that's it. Over x plus 1 times x minus 2. Again, the point of leaving this denominator in factored form is that the numerator might be something that itself factors and might share a common factor with the denominator. So let's see, does that happen here? Let me see if I can give myself a little more room. The numerator, certainly I can pull an x out. But is that completely factored? No, right? This guy right here, x squared minus 1, that's a difference of squares. So I can factor that further. So x plus 1 times x minus 1 over our common denominator. And voila, x plus 1 showed up in both places. So we can cancel that. And now we have as our rational expression answer in lowest terms, x times x minus 1 over x minus 2. Okay, the factored form is frequently going to be helpful in the future. Again, if you want to extend it all the way out or expand it all the way out, that would be x squared minus x over x minus 2, just doing that multiplication there. Okay, but either one of those is fine. All right. Now, we've seen several examples of adding rational expressions. What about subtracting rational expressions? Well, it turns out this is no more difficult than adding. In fact, it essentially is adding, just with a negative thrown in. If we have the rational expressions, say, 3 over x plus 1 plus 2 times x squared minus, well, let's say plus x. If we had this sum and we change this to a minus, all right, so now we're looking at the subtraction of two rational expressions. That's absolutely identical to 3 over x plus 1 plus a negative 2 over x squared plus x. Okay, so we just turned our subtraction problem into an addition problem, and then we proceed exactly as we did before. Of course, if there's more than just one term up here, we'd have to distribute that negative across, but that shouldn't be shocking. Okay, so then we would say, well, is our denominators in factored form? The first one is. The second one, not so much. We could pull an x out and get this. We still have the negative 2 up top. We ask the question, what's this guy missing that this guy has? Looks like an x. So let's put in an x over x right there. Clean up the writing there a little bit. And then we have 3x minus 2 over our common denominator. And we're essentially done, unless you want to multiply that denominator out. Okay. All right, so subtraction is no more difficult than addition. You simply add the fractions and distribute a negative across the numerator there of the second guy. Okay, so those are some examples of adding and subtracting rational expressions.